Implicit differentiation. What if we wanted to know the derivative of any point on the unit circle? Well, first of all, we see that obviously the circle is not y as a function of x. This fails the vertical line test. However, we could solve this for y. We've got y squared equals 1 minus x squared. And if we square root both sides, we've got plus or minus the square root of 1 minus x squared. So we could express this circle in terms of two different functions. The upper half, the positive y's, as the square root of 1 minus x squared, and the lower half, the negative y's, as negative square root of 1 minus x squared. And you can see that if we looked at it, this is as semicircles, these two different pieces, that each of these does pass the vertical line test there. Y is a function of x. We then could take these functions and we could find the derivatives, so we could find the slope of the tangent to the curve at any given x. So let's do that for this first function. First of all, I'm going to express this function. The square root of x can be expressed as a 1/2 power. That way I can use a power rule and a chain rule to find this derivative. So y prime is going to be power out in front. Decrease the power by 1. Well, 1/2 minus 1 is minus 1/2, but then we've also got the chain rule multiplied by the derivative of what's inside, which would be negative 2x. These two negatives and this 2 in the denominator and this 2 would cancel, and so I am left with x over, I could express this moving it down to get rid of the negative exponent and writing it back in radical form, square root of 1 minus x squared. And similarly, I could find this derivative and it would be the same as this derivative except for the negative sign, because I didn't start with a negative here. So I only have one negative in this particular step and have a negative on here. So I can express the derivative, but I've got two different derivative functions. One for if we are looking at the upper half of the circle, and one for if we're looking at the lower half. So if we wanted the slope of the tangent line to the curve at x equals 1/2, we can see that as we moved along this curve, as we start here at the left, we have a vertical tangent, but then as we move along, we actually have two different tangents as we look at various points along this circle. If we looked at this specific point where x equals 1/2, there are two different slopes of tangent lines depending on if you're in the upper half of the circle or the lower half. And so because we have these two different formulas for derivatives, if you were in the upper half, we would use this formula, and when we put in the 1/2 and we simplified it, we would have negative 1 over square root 3. If we put the 1/2 in this one, we would have 1 over square root 3. So we've actually got two different places here, and we've got to worry about two different derivative functions. Doable, but not the greatest. Now here is an equation, and if we looked at the graph of this equation, you can see this definitely is not a function, but we could break this up into three different pieces, each of these pieces being a function. This first one, this magenta, if we call this one f of 1 up to the point A, and then this blue one f sub 2, and then the yellow one f sub 3, each of these would be functions. We could then use our rules of derivatives and find the derivatives and find the slopes of the tangent lines to the curve at various points. We see if we were looking at an x naught here, we would actually have to put this in all three of these functions and have three different slopes depending on which part of the curve we were talking about. Well, you can see as our curves get more complicated that this would get harder to do. So we're going to want a better way to find derivatives of graphs such as this, that this one is be fairly difficult to solve for y and express y as a function of x and trying to find these pieces. In the early to mid 1600s, these French mathematicians were working on these kinds of things, and this particular curve I showed you was first proposed by Descartes in 1638, an incident with when they were developing calculus, and Descartes challenged Fermat to find a tangent to the curve at an arbitrary point, because Fermat had recently discovered a method for finding tangent lines, and he solved the problem easily, and this was something that Descartes was not able to do. So they call this the volume of Descartes, and we could show that the point 24 lies on this curve, but being able to find the tangent and the normal to the curve there was something that Descartes was not able to do, and Fermat showed him how to do that. Now, before we actually apply it to this particular curve, then we're going to revisit our unit circle and figure out how to do it there, and then we will come back to this. So we have our unit circle expressed as two different functions, but instead of doing that, we are going to look at it as our equation of our unit circle, but thinking of y as a function of x. So if we're looking at a derivative, because when we want the slope of the tangent, we're looking at the change in y over the change in x, and so we want to look at y as a function of x. So I've written it like this to emphasize that fact, and we are going to use what is called implicit differentiation. We are not going to solve explicitly for y and list y as a function of x, but instead we're going to take derivatives, but remembering that any time we have y involved, y is a function of x, so essentially we will have a chain rule. If I differentiate this first term, I get 2x, and then I have plus. If I differentiate this, this is a power rule chain rule because it is the function y of x inside of the squared function. So I have 2 y of x, and if I decrease the power by 1, this would just be the 1, but then I need to multiply that by the derivative of this function that's inside. Well, what is the derivative of y of x? Well, it's just dy dx, and then the derivative of 1 is 0. So now I actually have an equation that involves this derivative that I wanted to find, but it's not explicitly solved for dy dx, but I could easily do that. So I'm not going to write this of x part. We just know y is a function of x. Let's solve this for dy dx. So we would move the 2x term over and then divide by 2y. So that would leave us negative x over y. So this particular equation for the derivative function involves both x and y, but we could now easily compute the slope of the tangent to the curves at any given xy point. And the nice thing about this helps us then identify where we are. So we wanted the tangent to the curve at x equals 1/2, and of course in this equation, if x equals 1/2, and of course we get y equal plus or minus square root 3 over 2, which of course these were points on our unit circle. So there are two different places where x equal 1/2 on this circle, and now if we want the derivative there, we can simply substitute the x and the y in here and we would have the derivative. So the slope of the tangent at one of the places is negative 1/2 over square root 3 over 2, which simplifies to negative 1 over root 3, which is exactly what we had when we used this piece for the upper half of the circle. And similarly, if we subbed in the piece from the lower half, it would be the equivalent of subbing in here, and we would get a derivative of 1 over square root 3. This is much simpler to deal with, and so we could arrive at the derivative as a function of both x and y here. Now let's return to the volume of Descartes. First of all, if we wanted to just show that the point 24 lies on the curve, we would just need to substitute that in and verify that we have a true statement. So let's do that. And we see that in fact that does equal 0, because here we have 8 plus 64, so that's 72. And then if we multiply this, negative 9 times 8 is negative 72. So we can see that that does in fact equal 0. So the point 24 does lie on the curve. If we want to find the tangent there, well, first of all, we have a point, but we need a slope to find this tangent. So we would need to know the slope of the tangent at this point 24. So I'm going to use implicit differentiation here to find dy dx. The derivative of x cubed is 3x squared plus, now remember, y is a function of x, so I'm going to do a power rule, chain rule. So what that was is y is inside of this cubed function, so I did a power out in front, decrease the power by 1, multiplied by the derivative of what's inside, and what's inside was y, and the derivative of y is dy dx. Now looking at this next term, this is actually a product, negative 9x multiplied by y. So I'm going to need to use the product rule. The product rule says first times the derivative of the second is y, so the derivative is dy dx, plus the second, which is y, times the derivative of the first is negative 9. After I do the product rule there, I have equals, the derivative of 0 is 0. Now what I'm trying to do is figure out what this derivative dy dx is, and I see I have it in two different places, and so I am going to take the two terms that have this derivative and factor the derivative out. So that involved these two terms, factoring out a dy dx, and I'm going to move the other two terms to the other side. So I have 9y minus 3x squared. Now I can see that dy dx will equal 9y minus 3x squared. Dividing by this, I have 3y squared minus 9x. Now I could simplify this a little bit because I see that there is a 3 in everything, so I could factor a 3 out here and then cancel those. So that would leave me 3y minus x squared over y squared minus 3x. So here is an expression then that given any x and y, I could find the derivative there, which is the slope of the tangent to the curve at that point. Let's now evaluate this expression then at our point 2, 4. So this, putting a 4 for the y, is going to be 12 minus putting a 2 for the x, 4, over, we're putting 4 for the y, so that's 16, minus putting a 2 for the x here, so that is 6. So it looks like we get 8/10, which then would reduce down to 4/5. So our slope of our tangent to the curve at the point 2, 4 is 4/5. We can now find an equation for this by just simply using our point slope formula. So y minus the y from the point equals the slope times x minus the x from the point. So we have y minus 4 equals the slope, which is 4/5 times x minus 2. Now we could go ahead and simplify this. Solving this for y, we would have y equals 4/5 x, and this is minus 8/5 plus 20/5, so that would be plus 12/5. So here is an equation to a line tangent to the curve at the point 2, 4. Now if we want something normal to the curve, normal means that it is perpendicular to the tangent, and so it still needs to contain the point 2, 4. We would still use this formula, but the only thing we would do differently for the normal is we would take the negative reciprocal of this so that we would have a line that was perpendicular. So we will have y minus 4 equals negative 5/4 times x minus 2. So our line that is normal to the curve is going to be y equals negative 5/4 x, and this would be 10/4, which is 5/2 plus 8/2. So that looks like that would be plus 13/2. So here is our equation normal to the curve. Finally, we're just going to take just a minute and see what kind of interesting implicit curves we can get. We can kind of get some crazy looking things that would be pretty much impossible to try and express these as y as a function of x, but we could find slopes of tangents to the curves by using implicit differentiation to find the derivatives.